The next topic that we are going to discuss is conjugate heat transfer. Conjugate heat transfer is nothing but the ability to compute conduction of heat through solids, and it is coupled with convective heat transfer. So when we are solving conduction along with convection, that is conduction through solids and convection through fluid, that is referred to as a conjugate heat transfer. In that case, we have to use coupled boundary condition, and it is available to wall zones that separate two cell zones. So one side of the wall there is going to be solid, in which we are going to solve conduction. Other side of the wall is going to be fluid, and we are going to solve convection there. This is how we use the coupled boundary condition, as you can see here. We have discussed most of the aspects related to solving or user inputs related to physics of convection and conduction. What we are going to do is shortly review the material property input called as conductivity. By default, the thermal conductivity is considered to be isotropic. If you have to give something other than isotropic, like anisotropic, you have to specify it as a thermal conductivity matrix. There are different methods for it. We go into edit material of material properties of solids, and we select thermal conductivity as either orthotropic, or we can select different methods like cylindrical orthotropic, general anisotropic, and biaxial. We'll review one by one these four. First, we'll see what is orthotropic conductivity of solids, and it can be specified in cylindrical coordinates. We have to specify the axis origin and axis direction of a cylindrical coordinate system. Then we can specify three components: radial, tangential, and axial conductivity. So this is how we define cylindrical conductivity. The next way of, as we have specified, we are specifying cylindrical conductivity. The other type of conductivity is biaxial thermal conductivity. How do we specify that? Biaxial means one particular in-plane direction and the normal direction. So we just specify planar and transverse, and in order to specify anisotropic conductivity in three directions, then we have to specify all the 9 components of it actually. In order to specify the matrix component, you have to specify a matrix of the anisotropic conductivity. Once we have discussed three types of conductivities, material input, let us now move in and discuss one of the examples related to conjugate and heat transfer. This is a particular example of a cooling flow over cooling rod. These are the two rods. As you can see, they are solid rods, and this is the fluid. That is, rods are in yellow in color, and the fluid is blue in color. Solid is of aluminium. Water is coming in at 300 Kelvin, flowing through these rods. These are the properties of water. That is, density is 998, viscosity is 0.001, Cp is 4182, and conductivity is 0.6. It goes over these rods and goes to the outlet. We have to find out what is the flow pattern and what is the outlet temperature. Problem description is a 2D section of a cooling rod, and what we have to do is we have to find out the temperature distribution of both solid and fluid domain for following cases. Case 1, we are going to consider a constant heat flux of 1000 watt per meter cube generated in these rods. So 1000 watts is generated in the rods. All the walls except the common wall between solid and liquid as adiabatic walls. Preprocessing is simple. We have to consider the grid clustering and boundary layers. Where? So the question comes in, is the only since it's a 2D, it's a comparatively simpler case, but the problem is we have to consider boundary layer. Where do we have to consider boundary layer? Why do we have to consider boundary layer? These are the questions of intrigue. Boundary layer, boundary conditions that we are going to use for this particular cases: solids, basically for the zones, and fluid for the zone, and this is what you have to specify. Now, example of a boundary layer mesh is given here. Near all the conjugate heat transfer walls, we are considering a boundary layer. This is because we have to capture the thermal boundary layer, and we have to basically show that as the heat transfer is there from a solid to a fluid, we are going to construct thermal boundary layer and capture that heat transfer. So we have to consider finer boundary layer near the walls from which heat is coming from solids into the fluid. Boundary condition and zone types is clear here. The solid zones are given for the yellow region, and mass flow inlet is given for water flowing in. The outflow condition is for the water flowing out, and fluid zone is given for the entire blue region. All remaining edges will be wall. Edges between solid and fluid zone will also be wall but coupled. We have imported this particular grid, which is a hexahedral grid with a thermal boundary layer with a boundary layer mesh near the walls. This is the older Fluent version display, so you might see some mismatch with the current Fluent version that you are using. but this is what we are going to give. That is a solid fluid wall, which is a conjugate heat transfer, a double-sided wall. We are seeing the shadow condition also for that. This is the interior solid zone. Two separate interiors, one for solid and one for fluid, will be generated. Shadow wall is also generated for walls common in the fluid and solid zone, and the wall will be coupled by default. So this is the thing that we have to consider. Fluid zone is, this is the interior of the fluid zone, this is the solid zone. First step is select the model. For that we have to go to define model solver. We are going to select segregated solver. Then we are going to activate the energy equation also. This is the older fluent display, older fluent version display. So don't be surprised with the mismatch with the current fluid